Good evening, everyone. Are you able to hear me? Okay. So I think let us start the session. So today we will deal with the week 3 problems. So in week 3, what are all the things we have covered? Group, subgroup, and related theorems, and so on. So, okay, before starting, let me introduce myself. I am Harsha from IIT Tirupati. So let me share the screen also. Can you see the screen? The screen is visible, right? So let us start today's session. Okay, so the last week, what we have learned is group. Mainly, we started with the group. Are you talking anything? Okay. So we started with the group, and we studied what is a subgroup also. We studied subgroup, and what is a cyclic group. So I hope you have gone through all the concepts already in the portal, and so a generator of a group. And so and so, and some theorems related to all these concepts. Okay. So I think let's go to the problems. So first problem is, let G star is given as a group. A group is given G with the operation star. So consider the following statements. First statement, H equal to set of all x in G such that x star G equal to G star x for all G in G. Okay. So the question is, okay, the statement is then H is an abelian group. And the second statement is, given CA such that set of all x in G such that yeah, please mute. So the the group CA is given like this, and the question is CA is abelian or not. So we have two statements. We need to check which of the above are true. We have two subgroups of the group G. So I think in the class, sir already covered these sections. That is the subgroup H and subgroup CA. He has already defined them. So, so you know already what is the name of this group H and CA. So the question is whether H is an abelian subgroup and whether C is an abelian subgroup. So anyone can answer?
Both are true, madam. Hello.
Both are true. Okay, let's
Because
see.
they follow the commutative property, na?
Okay, let us examine case by case. First one, let us see. Okay, A. What is the name of the group A? The group, group H has a name. The center. H is the center of H. Okay, we call the set H.
Hello. Who is this Rajalakshmi? Hello, madam.
Okay, whoever not talking or asking doubt, please mute yourself. It is a disturbance for others also. Okay, so the H is the name of the group H is the center of G. Center of G. Okay. So we need to check that whether H is abelian or not. So what is the condition to be checked for any two elements x1 and x2 in H? We need to prove that, or we need to disprove that x1 star x2 equal to x2 star x1. So if this condition is satisfied, we can say H is an abelian group. So what is the condition? This x1 and x2 in H. So H is defined to be the set of all elements such that x star G equal to G star X. For example, x1 in H means what we can say? X1 star G equal to G star x1 for all G. Correct? So, what we need to prove that x1 star x2 is x2 star x1. So, by the condition, we have x1 star G equal to G star x1 for every G in G. So, in particular, if G equals, I am putting G equal to x2. What we will get? X1 star x2 equal to x2 star x1. What does this mean? Abelian. H is abelian. Okay. Because we are taking any two elements x1 and x2 in H, and finally what we are getting is x1 star x2 equal to x2 star x1. Clear? So this condition, we need to prove this condition, and finally we prove this. Clear? So H is an abelian. Any doubt in this question? Answer? Anyone has doubt? Okay. If there is no doubt, let us go to the second B. So here B also, it seems like that x star A equal to S star X. That means a condition of commutativity falls here. But actually, this is not commutative. Why? Because this is particularly for an element A. It is not true for every element. Here we have used the x star G equal to G star X for all G in G. But here in the case, we are taking for some particular A. CA is for some particular A. So CA is not, means need not be abelian always. So let us see how it comes. So let us go to the B part. CA equal to set of all x in G such that x star A equal to A star x. Okay, here for all A in G condition is not there. In particular, I am taking, so let us see in the question. See, the question is given as G star be a group. G star can be any group. In this case, I am taking G star is a non-abelian group. Okay. G can be any group. So I am taking G star as a non-abelian group. That is non-commutative group. Now, let A, for example, A I am taking is E. E means the identity element. Identity of G. Now, what is CA? CA means CE. By definition, what is this? Set of all x in G such that x star is equal to E star x. So, what is the set? Set of all x in G which satisfies this condition, x star equal to E star x. Can anyone say what is this set? Okay, I will write one more time. Set of all x in G such that x star E means same as x, right? E star x is same as x.
So
X.
every element in X.
Every element in G. Okay. So this C is the set of all element in G which is identically equal to itself. That is same as the set G itself or the group G itself. So what we are getting is, in this case, if I am starting with a non-abelian group, CA I am getting as G. Basically, if I am starting with any group, I will get the CA, that is CE as the same group. But in this case, since I have taken it as a non-abelian group, here I am getting CA equal to G is non-abelian. Clear? So, what does that mean? CA is not abelian. Okay. So, what we can say is, in every case, the group CA need not be abelian. Clear? Any doubt in this B part? If you have any doubt, please clear now itself.
Okay, madam. No problem.
Okay. So I think let's go to the second question. So second question is a simple question. The set of all real numbers under multiplication is not a group since, so we have four options. Multiplication is not a binary operation. So second option is multiplication is not associative. And third option is identity does not exist. And the fourth option is 0 does not have inverse. So, which one is the answer here? So, the question is, we are taking the set of all real numbers under multiplication. That is R with the multiplication. You can say R with the multiplication. So, first of all, They are saying it is not a group, and if it is not a group, one of the condition of the group should not be satisfied. Okay. So which option is correct here?
0 does not have inverse is the correct option here, ma'am.
Yes, 0 does not have the inverse. We know that for under multiplication, what will be the identity usually?
1 will be the identity, ma'am.
Yeah, usually 1 will be the identity element. So if for any element x in R, the inverse will be x, 1 by x, x into 1 by x equal to 1. So 1 by x is the inverse of x. But in case of 0, it does not have a inverse. Okay. So all other the condition you can check. So option D is the correct answer here. Here identity exists because 1 belongs to real number. And multiplication is not associative. Is multiplication associative?
Yes, ma'am.
Ma'am, multiplication is associative.
Yeah, multiplication is associative. So this option is wrong. And also multiplication is a binary operation, right? Binary operation means if A and B are two elements, A star B also in the same set. So it is a binary operation also. So the only option which is wrong is means here in the question, the correct answer is option D. Clear? Any doubt here? So that is why under multiplication, if we are considering R minus 0, we will take it as always R minus 0 with the multiplication. Okay.
Yes, ma'am.
So question is if A belongs to center, then CA. So okay, let us just check that. Okay, in that case, CA will be up again, right? So the question is, if A belongs to the center, then what will be CA? So let me. If A belongs to center, that means if A is in H, what is our H? H equal to set of all X in G such that X star G equal to X star G equal to G star X. Okay. If A belongs to center, then what we can say A star G equal to G star A for all G in G. So in that case, we will get a CA is abelian. So we can see what is CA. CA is set of all elements in G, X star A equal to A star X. So since A belongs to H, we can say that A star G equal to G star A for all G in G. Correct? Okay, in this case also, I think it is not available. Okay, for example, suppose again I am taking G is a non-abelian group. G is non-abelian. In this case, what I am taking is CA equal to set of all x in G. So just by definition, CA equal to set of all x in G such that S star x equal to x star I. Correct? So the question was, if A belongs to the sender, what will be CA? If I am taking A belongs to the sender, that is A belongs to H. That means A satisfy the condition A star G equal to G star A for all G in G. This condition is satisfied, correct? That means all G in G belongs to the set CA. That means CA is identically equal to G. But if G is non-abelian, then we can say CA is again non-abelian, correct? So in that case also, CA need not be abelian. Is that clear? Okay. So let's go to the next problem. So the third question is, the inverse of I in the multiplicative group.
Hello, madam. You just make announcement. The people are.
Sorry, can you repeat? Sachin, can you repeat what you just said now?
You just make announcement, ma'am. All the people should mute their mic and videos.
Okay. Yeah, so I think better you turn off the videos also. Please turn off the video and mute yourself. And you can unmute at any time if you have any doubt. So let's go to the So the question is the inverse of I in the multiplicative group 1 minus 1 I minus I is. So the options are obviously the 4 options given here. B 1 minus 1, C I, and D minus I. Okay. So the group is given as 1 minus 1 I minus I. And so the group G star is equal to the set 1 minus 1 I minus I with the operation multiplication. Okay, these questions actually does not belongs to assignments. Like this is the concept related to week 3 and means the similar kind of assignment you have in the week 3. So you to solve the assignment, this problem solving session will help you. Okay, yeah. So let's come to the question. So G star is a group given like this. So the question is to find the inverse of I in this group. First of all, before going to the inverse, what is the identity here?
One is the identity element, ma'am.
Yeah, one is the identity. So if you want, you can just check the group, whether it is a group or not. First of all, you need to check the associativity, the closure property, and the identity and the inverse. So you can just do the all operation here, and you can just verify whether it is a group or not. First of all, here we are getting 1 as the identity. Now the question is to find the inverse of I in this group. Okay, so the inverse of I means I star, suppose A is the inverse of I, then I star A should be equal to A star I should be equal to the identity 1. So we need to find the A such that this condition is satisfied. Okay. So can anyone say what is the inverse here?
I guess minus I is the inverse, ma'am.
Yeah, minus I. We can just check what is I star minus I, which is equal to here star is the multiplication, usual multiplication operator, I into minus I, which is equal to minus I square. What is I square? I square is minus 1. So minus of minus 1 equal to 1. In the same way, you can check minus I star I also. Minus I star I, which is equal to minus I into I. Again, it is minus I square equal to minus of minus 1 equal to 1. So, what we are getting is I star minus I equal to minus I star I equal to 1, where 1 is the identity element. So, inverse of I equal to minus I. Okay. Here, this question, any doubt? Any doubt in this question?
No, ma'am.
Okay, so let us move to the next question. So, given a group with Z star, be a group where star is defined as, usually we have seen star is defined as either addition or multiplication or something like that. Here, for star, I am giving another definition. Star is defined as A star B equal to A plus B plus 1. Okay, so what we have is Z star with it. The operation star is defined as A plus B plus 1. So first of all, again here you can check whether it is a group or not. That is, this operation is valid, whether it is a binary operation, whether the closure property is satisfied, and so on. So that you can check. So here the question is, the identity element in the identity of the group is options are okay. So options are given like this. So what is the identity of the group Z under the operation star? So you can just try very quickly. And you can just write and like what is the definition of identity, and like that you can just write and solve the problem. Just try once. Any answer? Okay, minus 1. So let us solve the problem. Let us see whether the answer is minus 1 or not. So what is the, suppose E is the identity. Okay, then we should have A star E equal to E star A equal to A for every A in Z. Clear? So I'm taking the first equation, that is A star E equal to A. A star E equal to A. What is A star E? A plus E plus 1. Clear? Because star is defined as A star B equal to A plus B plus 1. Instead of B, we have identity E here. So A plus E plus 1, which is equal to A. So our aim is to find the identity E. So from here, what we are getting is A plus E plus 1 equal to A. Here the addition is the usual addition. So this A and A will be cancelled. E plus 1 equal to 0. That implies E equal to minus 1. Okay. So here the identity element is minus 1. That is, if we are giving E equal to minus 1 as the identity element, then A star E equal to E star A equal to A. for every element in set. Is that clear? So whenever you are saying set, you should not take it as granted the operation is addition or multiplication or something. So you should check how the operation is defined. So according to that, the identity will be changed. Because under addition, we have already seen that 0 is the identity. But under this operation, identity is -1. So for a set, identity is not fixed. It depends on the operation. Okay. Any doubt here? Okay, if you have no doubt, let us move to the next problem. Okay, before going to the next problem, here itself, we can see what is the inverse of an element. So the operation is given as A star B equal to A plus B plus 1. So my question is, what is the inverse of A in set? So how we will find the inverse? Suppose B is the inverse. So what we should have, A star B should be equal to the identity. Okay. Now, what is A star B? A plus B plus 1. And what is C here? Can anyone say what is C here?
-1, ma'am.
B.
Yeah, under this operation, -1 is E. So we need to find the inverse B of A. So we will take B this side. Here all the operations are addition or the usual addition. So what we can take is A, we can take out the other side. So minus A minus 2. So B equal to minus A minus 2 is the inverse of A. So here also we can see the inverse actually depends on the operation. Usually under addition, what we will say for A, minus A is the inverse. And if it is multiplication for A, 1 by A will be the inverse. But in this case, for any element A, minus A minus 2 is the inverse of A. Okay. Any doubt here? So these are all just like means just the basic concept, how the inverse or identity is defined and how we should use the binary operation in the group. Okay. Now let's move to the next question. So given a group G star, and A is an element in G is given. If order of A is 30, then the question is order of A power 24. So the group G is given and an element A in G is given. And it is given that order of A is 30. Order of A equal to 30. So the question is to find order of A power 20. Okay. So this is actually just an execution of a known formula. So can anyone say which formula we can use directly to get the answer? How can we find order of A power 24? is equal
2
to
power n, ma'am.
2 power
N. N or m square.
what is n here?
24? No. We should find the n only. So we can use options, then we can.
There is one formula to find the order of a power m if order of a is given. Do you remember this formula?
A
Is that-
power mn.
If order of a equal to n, then order of a power m equal to n by GCD of n. Is this formula? This actually already Sir has covered this topic. Okay, so you can just go to the lecture and see how it is coming. So this result is already covered. So here a is given and the order of a is given as 30. So what is n here? N is 30. So here it is order of a. Order of a is given as 30, right? And the GCD of mn. Here m is, so we need to find order of a power m. Then we should take GCD of m and the n. What is here m? M equal to 24. Okay, 24 and 30. Okay, so the answer is 30 by 6 equal to 5. In general, if we are getting like we don't know what is the set G and what. If set or something is given and an order of element is given by some calculation or something, or using this formula and all, using the substitution and all, we can find the order of a power 24. But here G is not non-group. We don't know. We are just saying some G is given and order of A is given. So here we can use the formula only. Other than this, just substitution, I don't think it will work. Okay, substitution also it will work actually, because yeah, substitution also it will work. For example, if we are taking a power 24 power 5, so it can be written as, so if I am taking a power 24 power 5, it can be written as a power 24 5, and maybe I think so. Maybe you can just, this is a power 6 into 4 into 5, which is equal to a power 30 power 4. So since it is given, so it is given a power 30 is given as the identity, right? Because order of A is 30. So a power 30 is identity. A power 30 is identity means which is e power 4, which is equal to identity. So, and out of all the 4 options, 5 is the minimum value. Order of a power 24 is the minimum value are such that a power 24 power are equal to identity. So we are getting out of the 4 options, 5 is the minimum value such that a power 24 power 5 equal to identity. So using the option also, we can say it is the order. Okay. Yeah, a power 24 equal to a power minus 6. But this a power 24 equal to a power minus 6, we cannot use it to find the. Okay, like that also we can find it. Okay, maybe I can explain that also. A power 24 equal to a power minus 6. This I can write it as a power minus 6 into 5 and a power minus 1 into 30 or a power 30 inverse. Since a power 30, a is order of a is 30, a power 30 will be identity. This identity equal to inverse. Sorry. Sorry. Okay, so what I want to say is, so whatever I have done the calculation, it is wrong. Since a power 24 equal to a power minus 6, maybe just some rearrangement of like this multiplication factor, just by rearranging the multiplication factor, maybe you can try. Using that also, we can prove that 5 is the order. For that, I think you may need to use this condition. A and A inverse will have same order. Okay, because a power 24 equal to a power minus 6, it comes, right? So obviously the inverse power means a power minus 1 is coming. So after some calculation, what we will get is some a power minus 1, some power n it will get it. So instead of a, we will get the order of a inverse. So order of a inverse and order of a will be same. Okay, so use this condition if you are using this one. So basically what I will suggest is just go through this formula only, because here you have given us 5, 30, 10 and 15. Suppose we have one more option E, none of this. So in this case, also, we can go by option by option, because a power 24 power 5 also we are getting as identity. So, but in that case, we don't know if one more option is there. We don't know whether any number less than 5 will be the order, because suppose 3 is there. Okay, using this formula, we got 5 is the smallest order, such that a power 24 power 5 is identity. Suppose some other 3 or something is there, and for a power 5 also we are getting a power 24 power 5, we are getting identity. And like that we can try all of the options, but we don't know whether there exists a smaller power n such that n less than 5 with the a power 24 power n equal to identity. So if such an option, none of this is here, one more option is there, we cannot completely say this is the correct answer. So you should go by this formula. So you will get the exact answer. Okay. Is that fine for everyone? Is the solution? Any doubt? Can we move to the next question? So the question is, order of so what is the answer here? A permutation in S3 is given. So I hope you know S3. What is S3? What is S3? S3 is the symmetric group. In general, we will say Sn is the symmetric group on n letters. The symmetric group also covered in the class. Let's say, we can say a symmetric group on 1, 2, 3, etc. n. What does this mean? It is the set of all permutations under composition operation. So what we will take is the set 1, 2, etc. n we will take, and permutation we have already studied. That is set of all bijection from this set to the set itself. Okay. So the set of all permutation under the composition operation is the symmetric group on n letters. So here we are getting S3. So first of all, let me write what is S3. Can anyone say what are all the elements in S3?
6.
Sorry.
6 permutation are there, na?
Yeah, 6 permutations. So okay. First one is identity permutation. 1 is mapping to 1, 2, 2, and 3 is mapping to 3. Okay. So next one I can say 1, 2, 2, 1, and 3, 3. Next one is 1, 3, 2, 2, 2 fixed, 3, 1. And the next one is 1 fixed, 2, 3, and 3, 2. Next one will be 1, 2, 2, 3, 3, 1. And 1, 2. Sorry, 1, 3, 2, 1, 3, 2. Okay. So these are all the possible permutations in S3. So the question is 1, 2, 2, 1, 3, 3. It is a permutation in S3. So what is the order of this in S3? So what is the meaning of the order? Definition of the order of an element.
A power n equal to e where n is the least possible positive integer, ma'am.
Yes. So order of A means least n such that A power n equal to identity. So we want to find the least n such that this element power n, that is composition we will take, n times composition we will take. At what n we will get the identity element 1, 1, 2, 2, 3, 3. That is our order. So can anyone say what will be the order of this element?
Ma'am, I guess 2 is the order of this element.
Yeah, because let us see the 1, 2, 2, 1, 3, 3. This is our, suppose this is our row. Okay. So from here we can say row power 1 is not identity. Okay. Now we will consider row square. Row square means row composite row. That is applying row 2 times. So what we will get? 1 is going to 2 and 2 is going to 1. 1, 1. And 2 is going to 1. 1 is going to 2. 2, 2. So this composition is just like the usual function composition. And 3 is going to 3. Again 3 is going to 3. Means 3, 3. So this is our identity in the S3. Okay. So row square is identity. That implies 2 is the smallest value such that row square is identity. 2 is the order of row. Okay, so option B is the correct answer. Is that clear for everyone? Last question. So like that, for any element, you can try. Okay, for example, if I am taking this element, suppose sigma equal to 1, 2, 2, 3, 3, 1. What will be the order of sigma?
Ma'am, 3.
Yeah, 3 is the order of sigma. For example, sigma is not identity here. And in next case, we can consider what is sigma square. What will be sigma square? One is going to
One goes to 3.
yeah, 1 goes to 3,
2 goes to 1,
2 goes to 1,
and 3 goes to 2.
3 goes to 2. So this is the sigma square. So this is also not identity. So 1 is not the order, 2 is not the order. Now we are going to 3. So what we need to do is sigma composite sigma square we can do. What we will get? 1 goes to
1 goes to 3.
under sigma square, 1 goes to 3. Again, one more
And-
sigma we are applying.
So 3 goes to 1. 1
3
goes
goes
to
to-
1.
Okay, 1 goes to 1, 2 goes to
2 goes to 2.
2 goes to 2, 3
3
goes
goes
to
to 3. 3.
okay. So everyone can just try like this. 1 goes to 3 and that sigma square is applied. Now we need to apply one more sigma to get sigma cube. So 1 goes to 3, 3 goes to 1. That is 1 goes to 1, 2 goes to 1, 1 goes to 2. So 2 goes to 2, 3 to 2, 2 to 3. So 3 to 3. So this is our identity. So clearly order of sigma is 3. Okay. So yeah, in that way, you can find the ordering of any element. So let's move to the, okay, any doubt here? Okay, let's move to the next question. Okay, again, we are going to S3. The question is true or false. This symmetric group S3 is cyclic. Okay, is the statement true or false? Anyone knows this answer? So S3, we have already given what is S3 in the above question. So if you know what is the definition of cyclic, you can easily say whether it is a cyclic or not. So any guess?
Yes, it is cyclic.
It is cyclic. Okay, let us see what is the definition of cyclic. Cyclic,
Ma'am, every element generated by a single element to the power of integer.
every element.
Every element in the group generated by a single element.
Yeah, that means a single element generates the whole group. So there
Yeah.
should exist an element in A. Suppose there exists an A in G, such that the generator A generates means we are taking all the powers of A square, A cube, etc. So it should be equal to G. So in that case, we can say G is cyclic. Correct? So we need to check whether S3 is cyclic or not. So what we need to prove that we need to check that whether there exists a row in S3. Does there exist a row in S3 such that the generator row is same as S3. So this is our question. So to check the whether cyclic or not, this is the equivalent statement question. Okay, okay, not cyclic. So can anyone find a row like that? The row generates full S3. We have already listed all the elements in S3. We can see here. So this is the S3. Okay. So can any of this element generate full S3? If possible, which element will generate? Okay, let's go case by case. First element, let us see whether this element can generate S3, 1, 2, 1, 1, 2, 2, 3, 3. This is the identity element. Whether E can generate S3.
No, ma'am.
No, because let us take identity element equal to 1, 1, 2, 2, 3, 3. So whatever the power we are taking e power n, it is equal to e only. So other than identity, we have so many elements in S3, right? So whatever the power we are taking, we are always getting e only. So e cannot generate S3. Now, next element is 1, 2, 2, 1, 3, 3. Row. Whether this can element generate S3? That means if I am taking all raw power n, suppose all raw power n should be equal to G. Is this true? What is rho square? We have already proved what is rho square. Order of rho. Order of rho is 2, right? So what is rho square?
Identity element, ma'am.
Identity.
1, 2, 3, 1, 2, 3.
Yeah. Now, what is rho cube? Rho cube means rho into rho square. That is rho into identity, which is equal to rho, right? Now, what is rho power 4? Rho into rho cube. That means rho into rho square. Sorry, rho into rho is equal to rho square. And rho square we know it is identity. So, whatever the power we are taking, we can say first it is rho, second power it is identity, third power it is rho, fourth power it is identity, correct? So, set of all rho power n, what we can write it as contains rho and identity. Okay, so the element itself and the identity element also. Okay, is this clear? So it is not equal to the full G or Sn. Our G is Sn here. Okay, so this case is also discarded. That means rho cannot generate full. Now we covered 1, 2, 2, 1, 3, 3. In the same way, this is also what we will get is if we are taking this, its order is also 2. So what we will get is this permutation identity. This is the subgroup generated by this element. And the same holds for this elements also. Now let us go to 1, 2, 3, 2, 3, 1. Suppose sigma equal to 1, 2, 3, 2, 3, 1. So we already got sigma square as 1, 3, 2, 1, and 3, 2. Okay. What is sigma cube? What is sigma cube? We have already done that, right? 1, 3, 3, 1.
Identity, ma'am.
Yeah. 2, 1, 1, 2, 3, 2, 2, 3. So sigma cube is identity. So after this stage, if we are again going to take sigma power 4, what we will get? Sigma cube into sigma. That is equal to sigma. Okay. So what we are getting is again the case is going to repeat. Sigma power 4 will be sigma. Sigma power 5 will be sigma square, and so on. So the subgroup generated by sigma contains sigma, sigma square, and identity. Again, repeating means we are repeating the elements again and again. So this contains only 3 elements. So this is also not equal to Sn. Clear? Not
Yes,
Sn,
ma'am.
S3. Okay. So we in the same way, one more element, this element sigma square is also there. So you can the last element, okay, the last element in Sn, that also you can write. For that also we will get the order of that element is 3. So in that case also we can say it does not generate full S3. So there does not exist any row in S3 such that rho power n equal to 6, or we can say is generator of rho equal to Sm. Okay, is this clear? We can go through all the rows in S3 and we can see whether it generates S3 or not. So S3 is not cyclic. Clear? Any doubt in this question? Anyone? Any doubt here?
Madam, why you should not check another element in the group? Only check identity and row schema. But for
Okay.
other element,
The reason, actually, you
The
can
reason?
check. Actually, we should check every element. Why I am
Okay.
checking this element? Only two elements. These are the two types of elements. See, in S3, what I have taken first identity I have taken. Second, I am
Okay.
taking 1, 2, 2, 1, 3, 3. In
Okay.
the third one, you can see that this element is actually almost same as this element, right? Here 3 is fixed. Here
Okay.
2 is fixed. 1 is
Okay.
going to 2, 2 is going to 1. In the same way, 1 going to 3, 3 going to 1. So if two
Oh.
times we are applying this element, in the same way we will get the identity.
Okay. Okay.
So this belongs to the same type of element, that is order is 2 here. So I
Okay.
checked for this in the same way, it will also fall. That is why I am leaving this. You can just try these two. In the same way, 1, 2, 2, 3, 3, 1. This is this kind of cycle. 1 is going to 2, 2 is going to 3. A cycle of this is equal to, we can write it as a cycle 1, 2, 3. Okay. Here we
Okay.
can write it as a cycle 1, 3, 2. Okay. So both
Oh.
are of 3 element cycle. So whatever the operation we are doing, just the number only changes. The way of
Okay.
operation or whatever the order, it is going to be same. So that is why I am taking two particular cases from each cases. Okay.
Oh. Okay. Okay, madam. Thank you. I understand.
Okay. Now let's go to the next problem. So I'm taking S equals 1, 2, 3, 4 and F equals the permutation. 1 is going to 2, 2 going to 3, 3 going to 4 and 4 going to 2. One is going to 1, 2 going to 3, 3 going to 4 and 4 going to 2. So then F inverse equal to. So the question is to find the inverse of F. So what will be the inverse of F? F composite F inverse should be the identity. So we need to find the F inverse which is satisfied this condition. Inverse of composite F. Okay. So can anyone say what will be the F inverse?
1, 2, 3, 4, 1, 4, 2, 3, ma'am.
Okay, this is satisfied. 1, 2, 3, 4, 1, 4.
2, 3, ma'am.
1, 4, 2, 3. Okay, let us just see whether this answer is correct or not. So what will be the F composite F inverse? F composite F inverse means first we will apply F inverse, then F. So here 1 is going to 1 and then 1 is going to 1. So 1 is going to 1. 2 going to 4, 4 going to 2. So 2 going to 2. 3 going to 2 and 2 going to 3. So 3 going to 3. 4 to 3 and 3 to 4. So finally 4 to 4. So this is the identity. Correct? In the same way, you can check F inverse of composite F also. So usually this kind of problem will have options. You can select from options. Other than also, if you want to find directly F inverse, the only thing is we just need to interchange the two rows here. So here F is 1, 2, 3, 4, 1, 3, 4, 2. So in the F inverse, what we will take is this second row we will take as the first row. That is 1, 3, 4, 2, 1, 2, 3, 4. Then we will arrange in the ascending order 1, 2, 3, 4. So let me write it as F equal to equal to 1, 2, 3, 4, 1, 3, 4, 2. So this is our question. So F inverse will be, we will write this 1. So basically what we are doing, the process of inverse. So whatever domain will change to codomain and codomain will change to domain, right? So here, this is our codomain or range. It will change to the domain. So 1, 3, 4, 2. And then what are all the inverse image of that? That will be the map under F inverse, right? 1 going to 1, 3 to 2, and 4 to 3, 2 to 4. Okay, this is not the way of writing as a permutation. We will write the permutation in the order, that is in the order 1, 2, 3, 4. So we can write it as 1 is 1. Here 2 is going to 4. So 4 and 3 to 2 and 4 to 3. So this is how you can find F inverse. So this is the same F inverse 1, 4, 2, 3, 1, 4, 2, 3. Correct? So inverse of a permutation you can write like this. Clear? Any doubt in this question? Anyone? Okay, if you don't have any doubt, let's go to the next problem. The question is, okay, question is to find the number of elements in Sn. Sn, we already know what is Sn, the set of all permutations on n letters, 1 to etc. Sn. So the question is to find the number of elements in Sn. So any answer, any guess?
N factor.
N factorial. Okay, let us see number of elements in Sn. So Sn contains all the permutation, right? So number of elements in Sn means number of permutations in n letters. So Sn is the collection of all permutation. So if you want to find the number means we need to count all the permutations on n letters. So what is permutation? Permutation is same as the number of bijection on the set of n elements. Number of bijections on, let us say set of n elements means 1 to etc. n. So to find the number of elements in Sn, it is same as finding the number of bijections from 1 to etc. n. So how many bijection will be there in 1 to etc. n? Let us see. 1 to etc. n. So we need to find the bijection from 1 to etc. n to 1 to etc. n. Okay, bijection means 1, 1 onto maps. So if I am taking 1, under F, 1 can be mapped to any element 1, 2, etc. n. It's not every element, 1 of 1 to etc. n. Write it. 1 can be mapped to 1 of elements in 1 to etc. n. Okay, so this 1 has n possibility of mappings here. Okay, so 1 can be mapped to 1 or 1 can be mapped to 2 or 3 etc. n, any of this element. So we have n possibility here. Now second element I am taking, second one. So now for the second element, we cannot take all the elements here, all the n here, because 1 is mapped to sum of element k. So 1 is mapped to f of 1 already. This f of 1 belongs to this set. So to that f of 1, we cannot map 2 because f is a bijection. So this 2 can be mapped to one of elements in 1 to etc. n minus f of 1. Okay. So from here, we have only n minus 1 choices. So we removed the element to which 1 is mapped. So 2 can be mapped to the one of the remaining n minus 1 element. So in this way, 2 can be mapped to n minus 1. That is, the mapping of 2 have possibility, n minus 1 possibility. Now in the same way, 3 have how many possibility? F of 3 can have
n minus 2 possibilities.
yeah, n minus 2 possibility. 3 has n minus 2 possibility. Because we should exclude the case f of 1 and f of 2 since f is a bijection. So remaining n minus 2 possibility. Okay. So we can see the pattern. For 1, we have n possibility. For 2, n minus 1 possibility. 3, n minus 2 possibility. In the same way, if I am taking n minus 1, so f is from 1 to etc. n to 1 to etc. n. I am taking the element n minus 1. So n minus 1 n will have how many possibilities?
2 possibilities.
Yeah, that means n minus 2 possibility. So here 3 means n minus 3 minus 1 possibility, right? It is 1 possibility.
N minus 1 possibility is correct, ma'am.
Yeah, correct. N minus 1 possibility is 1 possibility. So then what will be the possibility for n? Sorry, n
Ma'am,
minus 2, sorry, 2 it is.
N minus 2, ma'am. N minus 2.
N minus 2 possibility. For 3, it is n minus 3 minus, okay, sorry, 3. 3 means 1 number less. So n minus 1 means it is n minus 2. So n minus 1 have n minus 2 equal to 2 possibility. And in the same way, n will have n minus 1 equals 1 possibility. Okay, so all together we can have f n into n minus 1 into n minus 2 etc. 1, which is equal to n factorial possibility to find a function, means to find a bijection. Okay, so what we are listing here is what are all the possible maps. So we are getting for each element we are getting how many possibilities. So if you are taking all the multiplication of all these means for full set how many mappings are possible, correct? So this is the n factorial possibility. So the cardinality of Sn is the number of permutation or number of bijections in an element is n factorial. Okay. Is this okay for everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now the next question is, if G star is a group and H star and K star are 2 subgroups. So we have already known what is a subgroup. We are taking G a group and under the same binary operation, G star and K star are two subgroups we are taking. Okay. So we need to check the true or false. H union K is a subgroup of G. So is this true or false? Is this question? G is a group.
False.
Okay, it is false. Okay, this is a false statement. So let us see why it is false. Like false means we need to give a counter example. If some statement is true, we need to prove it in general. False means we just need to give one counter example. So let us take G equal to G star means Z under addition. Z is our integer group under addition. And I am taking H. H is a subgroup 2Z under addition and K as 3Z under addition. Okay. So 2Z under addition means 2Z means set of all even numbers, set of all multiples of 2. So it will contain 0, 2, 4, etc. and the minus 2, minus 4, etc. And the 3Z under addition means set of all multiples of 3. That is 0, 3, etc. and 0, minus 3, etc. altogether. So here H and K are subgroups of G. Anyone have doubt in this? H and K subgroup of G.
Madam, why we are taking the integer group only? Not other.
Any group you can take. Only thing is you need to prove it is a false. Like whatever this is, it is false. So we can take any group such that H union K is not a subgroup. If you have any other example, you can tell, we can write that also. Okay. Okay, now let us just go with this example. So why I am taking this group is, I need to prove it is false. So I need to find suitable groups H and K such that H union K is not G. Okay. Sorry, H union K is not a subgroup. So what will be H union K? H I have -4, -2, 0, 2, 4, etc. And K is -3, 0, 3, 6, etc. So H union K will contain all the multiples of 2 and 4. For example, I can write it as -4, -3, -2, 0, 2, 3, 4, 6, etc. Clear? So this is our H union K. Is this H union K is a group? H union K group. So this is the H union K, and the operation should be the addition because we are taking the addition everywhere. So is this a group under addition?
No, madam, no.
No.
No,
What is the reason?
If we take the two elements 2 plus 3, it is not 5 there in the group.
Yeah. 2 plus 3 I am taking 2 and 3 in H union K. But it's addition, that is under addition, it is not closed. It does not belong to H union K. So H union K is not a group. Okay. So H union K is not a group means it is not a subgroup of G. So the statement is false. Clear? The only thing is we need to take subgroup such that its union is not a subgroup. So any group G you can start with, and any H, any K you can take. Only thing is H union K should not be a subgroup. So that is what we want to prove here. Okay. Now is H intersection K a subgroup? Not in this example. In general, I am asking.
Yes, ma'am. It is
Yes,
subgroup.
Yeah. So I think it is already covered in the section. Anyone wants the proof H intersection K is a subgroup? Anyone wants the proof of this? Okay, so you can just go through the lecture note. I think proof is there. So H intersection K will be a subgroup. Okay, here what is H intersection K? Here H equal to 2Z and K equal to 3Z. Just let us try what is H intersection K. So it is given here H and K. What will be H intersection K?
-6
Yeah, -6.
+6.
Yeah, so all the multiples of 6, -6, 0, 6, etc. Why this all the multiples of 6 coming? Here all the multiples of 2, here all the multiples of 3. So all the common multiples of 2 and 3 will be in the intersection. We are taking the intersection. So in the intersection, whatever the element belongs to H intersection, say if X belongs to H intersection K, then X belongs to H and X belongs to K, right? So X should be a multiple of 2, some 2T, and X should be a multiple of some 3S, some multiple of 3 also. Okay, so what does that mean? X is a multiple of 2 and 3. So the least common multiple of 2 and 3 is 6, right? So X should be a multiple of 6. Okay, so that is why we are getting H intersection K as the all the multiple of 6. This is our 6 set. Okay, fine. Okay, now next question is the number of generators of Z under addition. So we already know what is a generator. Generator means K is a generator. Then all the powers of A, set of all A power n if I am taking, it should be equal to the group Z plus. That is the that is what is mean by generator. So the question is the number of generators of Z plus. So options are, this option is infinite. 1, 2, 3. Okay. So we need to find how many generators are there for Z plus. Anyone knows any idea? Can anyone say any generator of Z under addition?
1.
Yeah, 1 is a generator because I am taking 1. What we need to find is 1 power n. Here operation is addition, right? So 1 power n basically means 1 plus 1. So instead of 1 power n, we can write it as n times 1. N times 1, right? So what we are doing is here we will take 1, then 1 plus 1, 1 plus 1 plus 1, etc. Okay. So and in the same way, what we need to do is all the inverse also. So 1 power minus n also we need to consider. Okay, 1 power minus n means all the inverse. So we will get 1 minus 1 we will get 1 minus 1 minus 1 we will get. So all that possibility, or otherwise you can say it as in this one what we will get is 1, 2, 3, etc. Okay, obviously generator is a group, so its inverse should be there. So its inverse means minus 1, minus 2, minus 3. All these elements should be there, and also its union 0 identity should be there. Okay, so what does this generator 1 mean? Set of all n1 such that n in Z. Okay, which is same as Z. Okay, so 1 generates the full group Z. Clear? Now, we got one generator of Z plus. Does there exist any other generator?
-1.
Yeah, -1. Because if I am taking -1, I will generate -1 will generate -1 plus -1, which is -2, and -3, and so on. So on the other side, -1 minus -1, what we will get? 0, we will get 1, 2, and so on. So okay. So all these elements contribute to Z. That means generator -1 is also Z. Clear? Now, does there exist any other generator for Z? Other than
No,
1
ma'am.
and no. For example, suppose if I am taking identity 0, okay, what is the generator of 0? Just the element 0, correct? So it is not certain, not equal to certain. Now I am taking any element other than 0, 1, and -1. Say, for example, I am taking 2. What are all the elements generated by 2? All the multiples of 2, -4, -2, 0, 2, 4, etc. Correct? So this is not equal to certain. So the generator of 2 means all multiples of 2. That means one odd numbers does not belongs to this one. So it is not equal to certain. If I am taking 3, what I will get? All the multiples of 3 only, right? Other than multiple of 3, we have element 1, 2, and so on. So in certain. So these elements are not included in the generator 3. So this is also not equal to certain. So any integer other than 1 and -1 does not generate a certain. So what we are getting is generators of Z are 1 and -1. Okay. So here the question is to find the number of generators of Z. So answer is 2.
Ma'am, I have one doubt, ma'am.
Yeah.
Ma'am, could you please tell me how one can generate 0 element, ma'am?
Okay, one can generate 0 element means generator 1 equal to set of all 1 power n such that n is Z. Okay. Since it is an addition, what is actually 1 power n? N times 1 such that n in Z. When n equal to 0, what I will get? N equal to 0 implies n times 1 equal to 0. So in that case, 0 belongs to the generator of 1. Okay.
Oh, okay, ma'am. Okay, ma'am.
So any other doubt here? Anyone?
n.1 or n plus 1 because it is additive na for
No,
0.
See, n.1 because what I'm saying is one in general for an element a in G, what we will write is a power n because a power n means a star, etc. star a n times we are doing. So here addition, that is a plus etc. plus a n times we are doing. Okay, if we are doing 0 times, that means we are not doing anything. This is same as n times a. Okay, 0 times means 0 times a. Here a is 1. That is 0 times 1. Is that fine?
Yes. Okay.
Okay. So any other doubt here?
No, ma'am.
Yeah, no doubt. Okay. So let's go to the next question. Check the following statement are true or false. So the first statement is Sn is abelian for all n greater than or equal to 1. And the second statement is order of 1, 2, 3, 4. Okay, these are the two statements. So first of all, Sn is abelian for all n greater than or equal to 1. So is this statement true or false? First statement.
Ma'am, it is obviously false, ma'am. The composition law is not commutative.
Yeah, it is not commutative. So for example, if we are starting with the, okay, you can start with the S1 and S2. For S1 and S2, it is actually some trivial cases it will come. So here in this case, it will be abelian. So do you want to check this now? Or you can check it later, S1 and S2. So we will start with the S3. Okay. S3 means set of all permutations in 3 elements set. So I'm taking 2 elements, 1, 2, and 2, 3. 1, 2, comma 2, 3 in S3. Okay. So if it is abelian, what will happen? 1, 2, 2, 3, and 2, 3, 1, 2 will be equal. Clear? So here, what is 1, 2, 2, 3? Okay. 1, 2 means 1 is going to 2, 2 is going to 1. And in this case, 3 is fixed. 3 is going to 3. And 2, 3 means 2 is going to 3 and 3 is going to 2. The cycle 2, 3. And whatever remaining, it is fixed. Okay. So from here, you can see what is 1, 2, 2, 3. First, we should apply 2, 3. This is our 2, 3. This is our 1, 2. So, what is the image of 1 here?
3, ma'am.
No, 2. Because 2, 3, we need to apply 2, 3 first. Okay. So, 2, 3 first means 1 is going to 1. And later 1 is going to 2. So, 1 is going to 2. So, in general, if we are applying F composite G, first we will apply G of X, and then we will apply F, right? So, first we need to apply the function 2, 3. So, 2, 3 means 1 is going to 1 and then 1 is going to 2. And what will be the image of 2? Two is going to 3, 3 is going to 3. And the image of 3 means 3 is going to 2 and 2 is going to 1. Okay, please mute. Okay, now if we are applying 2, 3, 1, 2, first we will apply 1, 2. So 1 is going to 2 and 2 is going to 3. It is 1, 3 and 2 going to 1, 1 going to 1 means 2, 1. 3 to 3 and 3 to 2. It is 3, 2. So obviously these two are different, right? Here the image of 1 is 2, here the image of 3. So this 1, 2, 2, 3 is not equal to 2, 3, 1, 2. That implies S3 is not abelian. So we got 2 elements in S3, which is not commutative. So S3 is not abelian. So actually Sn is not abelian for any n greater than 3. Abelian for all n greater than or equal to 3. Actually the same example will work for every Sn, because 1, 2, 2, 3 belongs to S3 means 1 is going to 2, 2 is going to 1, and the remaining third element is fixed, right? In the same way, if I am taking 1, 2 is an element in Sn, 1, 2 in Sn, and 2, 3 in Sn. Okay. In that case, 1 will go to 2, 2 will go to 1, and 3 going to 3, 4 going to 4, whatever the remaining until n, it is fixed. So in the same way, 2 going to 3, 3 going to 2, 1 going to 1, 4 to 4, etc. n to n. Okay, so we can take 1, 2 and 2, 3 as elements of Sn, and we can prove in the same way 1, 2, 2, 3 is not as 2, 3, 1, 2, not same. Okay, so because of that, we can say Sn is not abelian for all n greater than 3. Give me one. Yeah, sorry. So anyone has doubt here? Any doubt here? The proving the non-abelian of Sn. Okay, otherwise, let us move to the second one. The second one is order of this permutation in S4 is 3. So, is this true or false? So, directly just checking the permutation, you will be able to say whether this is order is 3 or not. Because it contains just one cycle. What is the order of this permutation?
3 only, ma'am.
Yeah, 3 only. So, this option is true. Okay, let me just write it as that's option B is true. Okay. So this permutation, you can see that it contains actually only one cycle. So what it actually means is 1 is going to 2. I can write it as 1 is going to 2 and 2 is going to 4 and 4 is going to 1. That is 4 is going to 1. So this cycle is completed and 3 is fixed. So we no need to write the 3. So 1, 2, 4. So if I am applying 1 times, 1 will go to 2. Second time I am applying, 1 will go to 4. Again I am applying means 1 will go to 1. So 1 is going to 3 cycle means 3 times the position is shifting. So 3 times position shifting means 1 will go to 1, 2 will go to 2, 4 will go to 4. And at every time 3 is fixed. So 3 always go to 3. So the order of, so whatever the length of the cycle, that will be the, that means if there is only one cycle, whatever the order of the cycle, that will be the order. Here order of permutation is 3. So if anyone has doubt, you can just write it explicitly. That is, write this permutation, find the square of which, and row square, row cube, like that you can see. And at what n, power n equal to identity, then that n is the order. So you can just try it explicitly if you want. Okay. Fine. This one, everyone. Okay, now let's go to the next question. Let G be the fold n by n matrices over Q. So options are finite abelian. Okay, this is group. Finite abelian group. The second option is infinite abelian group. And the third option is finite non-abelian group. And the fourth is infinite non-abelian group. So we need to check whether the given group is abelian or non-abelian, and also whether it is finite or infinite. So any idea what will be the answer? Okay, first let us check the answer.
Ma'am, obviously it is an abelian group because matrix addition is commutative.
Okay, it is abelian group. So does anyone have doubt on that it is abelian group? Because we are taking two n by n matrices and just adding entry wise, right? So addition is always commutative. So obviously it should be a abelian group. Now we need to check whether it is finite or infinite. Means does the group contains only finite number of elements or does it contains infinite number of elements? So what do you think?
Ma'am, I guess it contains infinite number of elements.
Yes, it is infinite group because we are taking all the matrices over Q, right? So Q means Q is countable infinite set. So there are infinite number of possibility to find the, because if I am taking some matrix, suppose it is 2 by 2 matrix, for example, ABCD I am taking. For A belongs to Q, B belongs to Q, C, all of this element belongs to Q. Okay, so each of the element can vary all over the Q. Q contains infinite number of elements. So actually it will have Q. This ABCD can have Q cross Q cross Q cross Q possibility. Okay, so infinite number of possibilities are there to find an element in Q. That element in group. So the group is infinite. So what we are getting is it is a infinite and a abelian group. So option B is correct, infinite abelian group. Is this okay for everyone? Any doubt here why it is infinite or why it is abelian? If you have doubt, please ask. Okay, then. Let's go to the next problem. One more question. I'm taking Sn. Here also I need to check whether it is finite or infinite. Abelian or non-abelian. So let us take n greater than or equal to 3. Because for n equal to, we have already, I'm taking n greater than or equal to 3. First of all, whether Sn is abelian, we have already done the question. For n greater than or equal to 3, whether Sn is abelian?
No, ma'am. It is
No.
non-abelian.
It is non-abelian. And whether it is finite or infinite, what it is Sn?
It will be finite, ma'am.
Finite, because cardinality of Sn, we have already proved it is n factorial, right? So it is finite. Sn is finite. So Sn is a finite non-abelian group. So earlier we got an infinite abelian group. Here we got a finite non-abelian group. Okay, let us move to the next problem. So find the generators of Z6 under addition modulo 6. What is Z6? What are all the elements in Z6? Z10, you have already studied what is Z10 under addition modulo n. So I'm taking Z6 here. So Z6 actually means the equivalent class of the operation plus n. So we can write it as 0, 1, 2, 3, 4, 5. So the 6 elements starting from 0. So what actually is under this Z6 with the addition modulo 6. So what is the operation addition modulo 6 here? Okay, for example, what is 3 plus 6, 5? What is this?
2.
Yeah.
2, ma'am.
Yeah, we will just add this element 3 plus 5, which is 8. So, what is the remainder of 8 if we are dividing with the 6? So, it is 2, right? So, we will take whatever the under addition, whatever the element we are taking, the corresponding element in this Z6 we will take. So, this is the, okay, I think you all know the Z6 and addition modulo 6. So, the question is to find the generators of the set of the group. Okay. So generator means the element A which generates the whole group Z6. So can anyone say what are all the possible generators of Z6? Is identity a generator?
One month.
Yeah, 1 is a generator. Okay. Let us see why 1 is a generator. First we are taking 1. 1. Now we will add 1 plus 1. 1 plus 1 is 2. And 1 plus 1 plus 1. It is 3. So I am taking all the orders of 1. That is set of all a power n. So next I am taking 1 plus 1 plus 1 plus 1, which is 4. Now next 4 times. Sorry, 5 times. 5. And in next 6 times. What is this value?
1 month.
1 is added 6
Zero.
times. Yeah,
0, 0,
0,
0.
0.
Yeah, this should be equal to 6 or equivalent 6 means it is 0. Okay, it is 0. So we again if we are adding one more time means we will get 0 plus 1. 0 plus 1 means again going to 1. So this cycle is going to repeat again and again if we are adding. Okay, so the generator of 1 means we are getting all the elements 0, 1, 2, etc. 5. So whole Z6 is generated. Okay. Now, in the same way, let us try all of the elements. So, for example, identity always generates only identity elements. So, in any case, in any group, we don't need to check the generator of 0 because it generates only the identity. Now, next is 2. Okay, can you say what are all the generators of 2? First one is 2.
1 and 5 are the elements.
1 and 5 are the
But
generators. Okay.
2 generators.
Yeah, 2 generators are 1 and 5. Okay, let us go through each and every case so everyone will understand. So, 2 is generators of 2. First it is 2. What will be the next generator? 2 plus 2.
4, ma'am.
4. Yeah, next 2 plus 2 plus 2 or 4 plus 2. What is that?
0.
0. Yeah. Again, if I am adding 2, again I will get 2, then 4, 0. Now this cycle is going to repeat, so I can close the set. It does not generate the set 6. Okay. Now if I am taking 3, what will be the generators of 3? First I will start with 3 and the next
3
element
and
is
0.
0. Again, repeating means 3 and 0 will be repeated again and again. So this is also just 3, 0. Now if I am taking 4, what will be the 4? Then 4 plus 4 is?
2.
2, ma'am.
Yeah, 4 plus 4 means it is 8. 8 in Z6 is 2. 4, 2, and 2 plus 4 is 6, which is 0. Again, repeating means same we will get. That is generator 4 and generator 2 are same. You can see here, right? Now, if I am taking generator 5, let us see what will be 5 first. Then what will be the next element? 5 plus 5, which is 10. What is 10 in Z6?
4.
4. Next element?
4 plus 5 is 9.
Ah,
3.
yeah, 3. Now 3 plus 5 is 8. It is in 2.
2.
Again 1 and 0. Okay. So here again we are getting Z6. So we covered all the cases 0 to 5. So we are getting only 2 cases 1 and 5 which generates Z6. So generators of Z6 is 1 and 5. Okay. There are 2 generators. Is this fine? Here actually you can see that this 1 and 5, like this 1 and 5 are actually relatively prime to 6, right? See here for 2 and 6 there exists a common factor 2, and for 3 and 6 there exists a common factor 3, and for 4 and 6 there exists a common factor 2. Okay, but for 1, 6 and 5, 6, what we are getting is its GCD is 1. That is the exact reason why this 1 and 5 generates Z6. So if we are going more into abstract algebra, set and plus and all, then you can see that maybe, I don't know whether it is covered in lecture or not. Actually, all the elements which are relatively prime to Z6 means 6 will be the generators of Z6. Okay. Any doubt in this question? Anyone? If you have any doubt, you can ask the question. Okay, you can ask now.
Madam, one more doubt, ma'am.
Yeah, yeah.
Madam, how to find out the distinct subgroups of a given group?
Okay, distinct subgroup. Like actually, okay, I will do with some examples. Okay.
Okay, ma'am.
If it is a cyclic group, actually, for every cyclic group, all the subgroups will be cyclic. So if it is cyclic group, you can find all the generators. For example, if Z plus is given, for this, all the subgroups will be in the form NZ with addition. That means we have already seen 2Z, 3Z, and so and so. Okay, that means 2Z is generated by 2, 3Z is generated by 3, and so and so. Okay, here actually Z is a cyclic group. So its subgroups will be the generators of elements in Z. So means I am taking an element of Z and finding the generator. So whatever I am getting, it will be a subgroup. So subgroup of a, sorry, Yeah, subgroup of a cyclic group will be cyclic. So you can find all the generators. All cyclic generators actually. Okay, in that way, for a cyclic subgroup, we can see. Basically, we will deal with cyclic subgroups. Otherwise, if I am okay, for example, if I am doing plain for group, do you know what is
Ma'am,
plain?
my doubt is total number of subgroups.
Okay, total number of subgroups.
Yeah.
Uh, total number of subgroup, I don't know, like whether there exists a formula or not. For example, if it is an infinite group, see, we have infinite number of subgroup, right? So,
Madam,
so
for a
now,
finite group,
yeah,
finite group, how
Hmm.
to find out the total number of subgroups?
I don't remember exactly whether such a formula for any finite number of subgroup exists or not. I think in general there is no formula. It depends on the, maybe for Zn plus n, we can find in how many number of subgroups are there. Some existing formula will be there. It is there. In the same way, for Sn also we can find how many subgroups will be there. But in general, for any finite group, I don't think there exists a formula. For a finite group, it depends on the group, how many subgroup it will have. So I think so. Maybe I will check and let you know the next time. Okay.
Okay, ma'am. Okay, thank you.
Thank you. Any other doubt or questions? Q power n minus 1. So are you talking about number of subgroups? No, I don't think in general for a finite group of n elements, 2 power n minus 1 is. I'm not sure actually. This is not true in general for every group, I think. I will check and I will let you know next week. Okay. So if you don't have more doubts, let us stop the session here and we will meet then in the next week. Anyone has doubt? Okay, shall we stop the session now?
For subgroup, we cannot say exactly it has these many subgroups because
Can you repeat?
no, the one person asked the doubt now.
Yeah.
We cannot say if we take some finite group, okay, each and every element is a subgroup. If you take single element also, it's a subgroup only. No, we can consider like that.
No. If I'm taking, so are you saying like if I'm taking any group, a single element is a subgroup of that group?
Yeah.
No. For example, I am starting with the, I'm taking Z6 again.
Madam, can we apply the quotients for finding subgroups?
1 minute, let me finish this. For 5. So if I'm taking a single element 5, it is not a subgroup of Z6, right? It is not a subgroup of Z6 because identity is not there in this set. So it is not a subgroup. Okay.
Yes.
Yeah. Okay. One more person was asking something. Can you
In the
repeat?
generator, only the subgroups.
In cyclic case, the generator are the subgroup. Here we are dealing with cyclic case. Actually, there are groups which is not cyclic. For example, Sn is a like it's not cyclic. In that case, there can be groups. Means the Sn itself is a subgroup, but it is not a generate. It is not generated by some element, right? So in cyclic case, we can say all the cyclic generators are subgroups. But in general, it is not true.
We cannot say.
Yeah.
Thank you.
So the other person, can you repeat the question?
Is there any method of can we find with the cosets, with the help of cosets?
With the
Any
cosets,
formula?
to find the subgroups.
Yes.
No, with the cosets, no, I don't think there is a formula. No, coset is just a kind of subsets only. Coset is not even a subgroup actually. So with that we cannot find. Let me just. Okay, for example, let me just try with the Z4 equal to 0, 1, 2, 3. Okay, the subgroup of Z4 is, first one is 0. Okay, and the next subgroup will be 0, 2. And the next one will be 0, 1, 2, 3. Okay, these are all the possible subgroups of Z4. Now I am considering the claim for group B. B is CA. Do you know this claim for group? So the claim for group is defined like this. An operation star with E, A, B, C. So the operation is defined like this. E star E, that is E is the identity. So E star E equal to E star A equal to A, then B, C. In the same way, here also A, B, C. And A star A equal to identity, and B star B equal to identity, C star C equal to identity. Okay. And A star B equal to C. Yeah. Okay. So this is
A star C is B.
A star C equal to B, and here it is BC. So this is, and sorry, not like that.
No, B star A is C. CB.
Yeah, this is CB, and this is A, this is A. Okay, this is correct. This is how we are defining the claim for group. Or it is, okay, here the subgroup of, let us check whether they have same number of subgroups. Set E is a subgroup. EA is a subgroup, right? Here I am taking, you can check the closure property. A star A equal to E. So whatever the operation I am taking, it belongs to this only. And the inverse of A inverse equal to A. Okay, identity is the inverse is the, it is closed. In the same way, EB is a subgroup and EC is a subgroup.
EC also subgroup.
Yeah, and EABC is a subgroup. So here we can say that both of Z4 and B have same number of elements, but the number of subgroup here it is 3 and here it is 2, 3, 4, 5. Correct? Okay, I didn't miss any subgroup here, right? Here number of subgroup equal to 3 and number of subgroup equal to 5. Yeah, anyhow, here clearly we can say this both are having different number of subgroups. Okay, someone asked the doubt about this only, I think, correct? Is that okay for you? This only you asked, right? Number of subgroup of is there any formula to find the total number of subgroups? So in general, there is no formula because even though it has same number of elements, since the operation, like whatever, the group is different, so the number of subgroup is also different. Is that okay? Who asked the question? Is that okay for? Any other doubt?
No, madam. Thank you.
Okay. So thank you, everyone. So let's stop now, and we will meet on the next week also. Let me stop the meeting.
Thank you, ma'am.
Okay, thank you.
Thank you, ma'am.
Yeah, thank you everyone.